So to kick off day 2, we have Iosif from right here, as everybody knows, telling us about microstate geometries, results, hopes, and confusions. Take it away.
Thanks. I've been organizing about 15 seminars since I came to Saclay, and I made it a matter of principle never to give a talk at a conference which I organize. And so Nick, at some point in spring, he said, "Oh, you gave a talk in Santa Barbara, people liked it, you should give a talk in the conference." And I was like, "No way," over my dead body. And then he kept on pestering me, and for about 2 months, I kept on refusing. And then at some point, I said, "Okay, this will be a review talk. I'll try to be more generic about, discuss things. But again, it's something which I'm, it's something which, again, I've never done before. And, it's blame it all on Nick if it doesn't work well. This is again work which has been going on here for the last many years. Those are my collaborators. The ones in blue don't have permanent positions. The guy in red is applying this fall. So if you want a good postdoc, remember get the names. The other guys are also many of them are in the market for faculty jobs, and there'll be market for postdocs in the future. So they are really amazing. We really have an amazing team here. So. Again, I'll begin very fast. This quantity knows everything. You know very well in string theory, you do Strominger of alpha, you count a bunch of strings that brings a zero coupling, you turn on gravity, you make this string bigger. The standard law is that gravity is an attractive force. Whatever stuff you're building becomes smaller. The horizon of the black hole becomes larger. At some point, the horizon engulfs it. This is called the Horowitz-Polchinski correspondence point, and you recover the standard black hole. And this has been, the game, the name of the game for many years in the field. However, what we have found is that some of these microstates of Strominger of alpha, some of the microstates of the D1E5 CFT, instead of getting a horizon, they actually become something like this. They become some geometries which look like the black hole from far away, but instead of have the same throat as a black hole, but they don't have a horizon, but they end up in a smooth cap. And the big question is it possible that, since some of the black hole microstates are like this, is it possible that maybe all the black hole microstates are like this, or, some subset of the black hole microstates are like that? And this has been put forth long before this work by Samir Mathur back in 2003. So the idea is that, the black hole horizon is just a result of course, graining over an ensemble of horizonless solutions, and, the states of the system are horizonless. And one can also argue that, again, replacing the horizon and putting something there is the only reasonable solution to solve the information paradox. This is argued by Samir Mathur and also by AMS. There are 2 more things in the market. One of them is ER-EPR islands. There will be a talk tomorrow. There will be discussion tomorrow. One thing which I don't like, but the guys in the islands community seem to be changing opinions every other month. The question is, are there non-localities in these islands proposals? What Juan told us is that there are non-localities of the scale m cube, which is 10 to the 53 the size of the universe. Now I'm getting a bit older. When you're young, people are more enthusiastic. I'm a bit conservative, so this is a bit too much for me. I'm getting older, so maybe younger people, they may enjoy it more, but at some point with age one becomes a bit more. These things already have no locality of the scale of the horizon. That's quite a lot. When I was young, this used to be the revolutionary thing. Now people do no localities at the scale of the universe times 10 to the 53, and without impunity. Back then, we're giving a hard time by just doing a non-locality at the size of the horizon. You can also do state-dependent operators to reconstruct the interior. This is non-Copenhagen. Again, I'm not that old. People who are past a certain age, as Linde told me at some point, I discussed about, multiple interpretations of quantum mechanics, and Linde said, this is what people do when they are close to retirement. So I'm not that old to get into non-Copenhagen, so I'm smack in the middle. And, this for me, at this point, at this age, this seems to be the reasonable way to solve it. Just to give an analogy, let me finish this and then, just to give an analogy with an ideal gas, you can describe the ideal gas in 2 ways. Using thermodynamics, PV equals nRT, you can fly airplanes. And the thermodynamical description is given by the black hole solution. This is just describing the air as an ideal fluid. But there's also statistical description using microstates, molecules floating around the room, going around, buzzing around, hitting us, and so on. This would be the microscopic description. And what we are claiming is that this is the microscopic description in terms of microstate geometries and fastballs, and the black hole solution, the nice, beautiful classical textbook, is the thermodynamic solution, which is good, to get entropy. You can get the entropy without having any idea that the air is made of molecules. You can get, you can get a lot of information. You can fly airplanes without knowing that the air is made of molecules. But if you want to do, for example, shot noise and other phenomena which need molecules, you need to know that the air is made of molecules. So if you want to do physics at the horizon, you basically need to use this description. You cannot use this one. This is the generic framework. I'm just giving you, and so this is again the way people want to do it. And people putting structure at the horizon is very in vogue. We heard yesterday all the talks about people trying to constrain it experimentally, and there are many proposals of things called the extreme extreme compact objects. You hear about these things, gravastars, quark stars, boson stars. There's a gas of wormholes. I heard at some point about the island coming out of the horizon and going around at some distance away from the horizon. You hear about quantum black boxes, soft hair, sometimes modified gravity, mirrors, floating on some pixie dust, Bose-Einstein condensates, everything and their brother. But there's a problem with all these proposals. They're nice proposals, and again, the urge is very good. It's the heart is in the right place. The heart is in the right place. The black hole horizon is horrible, gives information loss. One should do something else. So people are doing many proposals. People are working with them. The heart is in the right place, but one has to use a bit, the rationality and the part, the rational part of the brain. And the problem is, all these proposals, they are very beautiful, but they have some problems. If you want to replace the black hole horizon, you have to do much more work. So this is basically the first thing which actually Gary Horowitz first impressed upon me, and this is actually the way. So when Samir came with his proposal, I was in Santa Barbara, and Gary Horowitz said, these proposals, and every few years somebody comes and tries to replace the black hole horizon. So all these proposals have a big hole. They don't grow. If you want to replace the black hole with something, the something you build must grow with G Newton. It might actually become larger with G Newton. And therefore, Gary was saying that all these proposals are going to be garbage and trashed out because whatever you put to replace the black hole horizon doesn't grow with G Newton. Now, normal objects, again, gravity is an attractive force. You make G Newton stronger, gravity stronger, normal objects become smaller. The black hole horizon, on the other hand, to make gravity stronger, the black hole horizon grows. So you can never get something to basically, in some normal theory with normal matter satisfying normal conditions, you can never get something to replace the black hole for all regimes of parameters. Or otherwise, you can never get something to replace the black holes for all the masses. You can never get something, you can never build an object with normal matter and stuff to replace the black hole. However, if you use non-perturbative degrees of freedom of string theory, as you do for these microstate geometries, they basically are made of d-branes, which are solitons, which have a mass which goes like 1 over g string. And because G Newton is G string squared, when you make G Newton stronger and G string stronger, solitons become lighter, and therefore these things grow. And they actually grow exactly the same rate as G Newton. And this is something, this is the reason why I got into this, into Samir's proposal and into building these things. Because, essentially, we tried to kill it and it didn't die. This is Gary Horowitz's way of killing it, and, we checked out, all the factors of G string and everything, and it has exactly the right growth to replace the black hole for all values of G string or for all values of the mass. Nobody else, none of the other proposals do that. So, lesson number 1, to build structure of the horizon, you must use non-perturbative degrees of freedom, something which becomes lighter as gravity becomes stronger. You cannot do it using normal matter. Lesson number 2, you need a mechanism not to fall into a black hole. Why is that? Well, this is a Penrose diagram of a black hole. You're trying to put something there. This is the place where you're trying to put something, some structure, some fuzzball, some firewall, you name it, some boson star. Now, the problem is the horizon is a null place. And you see that, time goes up this way. So if you put something at the horizon, something has to be very strange. And, there's a GR dogma. You cannot put stuff at the horizon. And the reason is very stupid. Because the horizon is null, if you want to stay there, when you have some massive stuff, you want to put some protons or some neutrons or some stuff, you have to go with the speed of light. This red thing goes with the speed of light. If you let it, if it doesn't go with the speed of light, it falls in. So whatever you're putting at the horizon must go with the speed of light. So normal stuff falls in. Normal stuff, you just put it there, it falls in. And you cannot hide behind quantum and say, there are some quantum effects, all these quantum things, there is always a semi-classical limit, and in the semi-classical limit, they are going to fall in. You cannot build, normal stuff there. The stuff needs to be very stiff. And you need to have something which we call the support mechanism. And again, lesson number 2, if you don't have a support mechanism, it's not the right physics. You need to have some sort of support mechanism. Boson stars, for example, have a support mechanism. There's some flux, keeping them. There are many proposals which have a support mechanism. I'm not saying this is the only one, but what I'm saying is that people who just say, I put some quantum stuff and there's a support mechanism, this doesn't work. You need to have an explicit support mechanism. Problem number 3, again, problem number 1. And again, this is what's happening. This is stolen from Nick's slide. If you don't have a support mechanism, you're a bit like this Willy Coyote, which, essentially saying that gravity doesn't work until you look down. So, this guy goes and, basically starts going and, keeps on running and then, goes off the cliff here and then at some point looks down and says, gravity, poof. But, before that, it doesn't work. So this is a bit the situation if you don't have a support mechanism. Gravity is just going to suck you in. There is no no way to escape. Now, problem number 3 is even worse. Problem number 3 is that you are collapsing a shell of dust. Let's suppose I collapse a shell of dust, and let's suppose I have a huge shell of dust bigger than this, TON 618 black hole, which is the biggest, fattest black hole in the universe unknown. TON comes from some Mexican observatory which found this black hole. It's really the biggest, fattest thing in the universe observed so far, and it has 180 hours between crossing the horizon and hitting the singularity. So that's a lot of time. You have to go for 180 hours after you cross the horizon before you hit the singularity. So let's suppose I make a horizon. I'm collapsing some shell of dust, huge shell of dust, somewhere in the middle of the universe. I make this huge, super mega big black hole. Then the shell of dust, when you collapse it, it goes at the scale of the horizon, it forms a horizon. This was shown by Oppenheimer and Barbie back in Oppenheimer and Schneider, sorry, back in 1939. When you collapse a shell of dust, it makes a horizon. You cannot escape. So you make a horizon, and then the shell of dust keeps on collapsing for 180 hours. At some point, of course, it becomes small, stringy, strongly coupled stuff, and then you say, here, sure, no problem. Here, you can give me whatever stringy stuff you are giving me. You can let string theory take over. You can give me non-perturbative degrees of freedom. Whatever you want in string theory can come out in this red region. But what you need is to make something at the horizon. But the horizon is in your causal past already. By the time you make this red stuff here, by the time your shell of dust becomes strongly coupled and gravity becomes strong and you have problems, you're already 180 hours in the future of this region. So if you want to make something here, if you want to make some sort of firewall, fastball structure at the horizon, if you want to create some structure at the horizon and not create a horizon, you need to have some mechanism which allows you here to say, gravity, even if it looks weakly coupled, even if the curvature is as big as on the Earth, somehow gravity should be invalidated. Somehow gravity should break down at the scale here. If you don't make the structure here, you can only make it by going back in time, or by going at a space-like separation of a huge distance. 180 light seconds. That's a lot of space separation. You need a lot of very complicated physics to do that. And again, that's illegal. The way this has been proposed to go, so this is an argument which Samir made with Per Krause a long time ago, is that the black hole has a huge amount of microstates. The microstates don't have a horizon, but there are e to the s of them. And if you look at the shell of dust, they calculated and they estimated that the shell of dust can tunnel into these microstates, but there are e to the s microstates. The tunneling probability is e to the minus s, and therefore the shell tunnel probability 1. This was their argument, but the argument, it was a very nice argument, but the problem is there's no coefficient here. There's no e to the minus s. If this had been e to the minus s over 2, it wouldn't work. If this had been e to the minus 2s, it wouldn't work. So then we actually set up to do a calculation with Daniel and Andrea Pum and Berwick Nock long time ago, when Daniel was a grad student, so long before he ever got into into this area. When we calculated this tunneling probability for a bunch of M2 brains, so again, this is very near BPS, a bunch of M2 brains bubbling into super tubes, so it's a complicated calculation using this Denev quiver quantum mechanics and so on. And if you do this calculation and you compute the tunneling probability, what you find is that for this shell of M2 brains to bubble into to tunnel into essentially microstate geometries and fastballs at the scale here, you actually find a probability which comes out to be smack e to the minus 2s, e to the minus s. And the coefficient is really 1. It could have been, again, 1/2, it could have been 2, it could have been 7. It's not. It's really -1. It's exactly the right coefficient for this to tunnel. So for us, we took it as a serious, so this is, for us, is confirming that this intuition which Samir and Per Krause have is really the right intuition. It's really that, these solutions really have tunneling with the probability 1. And if you don't have e to the s horizon size microstates, again, if you want to say I'm forming structure at the horizon, if you don't have a huge entropy, if you don't have an entropy of order e to the s, you're not going to form it. So again, this is lesson number 3. Black hole entropy the structure must have. Otherwise, and this rules out, for example, gravity stars and many things. Yes, I mean.
So this argument seems a bit circular, that if you have e to the s microstates that are available at the horizon, then you can tunnel into them.
Yes.
You need the matrix elements for the tunneling to be big enough. Mm-hmm. It sort of assumes that there are e to the s microstates available at the horizon, yes, and then you do the calculation. But you still don't explain why there are e to the s microstates and why they're available at the horizon scale.
Sure, we need to build them. That's what I'm doing next. Absolutely, that's what I'm doing next. That's why I'm saying that if you want to build a structure at the horizon and you want to claim that I understand what makes a black hole, you have to build it to the S microstate at the horizon. If you don't build them and you just say they're going to be there, okay, great, how are they going to be? Can you calculate? Can you show, what structure they have and so on? So, that's what I'm saying. It's very important to, that we have to build them, absolutely. And that's exactly, that's why, on the next size, I actually say that, the only construction with its properties are actually 2.5. 2.5 because, again, we haven't built all of them. Is really that, we can really do these things in string theory using these things called microstate geometries. Essentially, they're like all these supersymmetric geometries, which look like a black hole, quack like a black hole. They have the same faraway region as a black hole. They have a long black hole throat, and then you go at the bottom and you find the cap. And those are actually, again, cohomogeneity 3 solutions, functions of 3 variables. So, essentially parameterized by infinity times infinity times infinity number of parameters. Horrible solutions. I'm not going to go into that. I don't know if anybody's talking about superstrata at this time. I mean, I think in the previous conferences there are many talks about them. But we call them superstrata. We're very happy about them, and they have many features which you expect from typical microstates. So, for example, when you have a long throat, there's a mass gap, and the mass gap comes out to be the one of the typical microstates. So, the superstrata, there's a nice, beautiful industry going on with that, and essentially we have been doing it in Saclay for since 2011, since we conjectured them. They're dual to states. So again, they look far away like the ADS 3 times S3, which you normally have. Then they have an ADS2 throat, and then instead of having a black hole, so in a black hole, the ADS2 throat goes on forever. Here it caps, and there's a microstructure at the bottom of this long throat, and this long throat can be super mega long. So this long throat can be, really, really long. And you can build a CFT dual states, you can solve the wave equation, you can compute geodesics, mass gaps, Weidmann functions, Green's functions, thermalizations, chaos, you can do a lot of things. You can really do a lot of things. And, you get the right properties of the typical D1D5 state. So, for example, there's a calculation by Raju and Srivastava, which is called the critique of the fast proposal, which computes some Weidmann function, but it computes them in the wrong regime of parameters. If you compute them in the right regime of parameters, it matches exactly what you expect for the black hole. So that paper should have been called a spectacular confirmation of the fast proposal, but they looked in the wrong regime of parameters, and hasta la vista. But if you're careful in computing, and you can really find Green's functions, you can compute 4-point functions, too light, too heavy, correlators, and so on, and you get exactly the properties you expect. Yes, you have, and then Roberto.
I understand that there is a difference between the typical microstates of the D1D5P black hole and the superstrata, which is the shape. I understand that the superstrata has a shape of a circular supertube and momentum waves outside, whereas I would have expected that the typical microstate of the black hole is roughly spherical.
I'll get to that, absolutely. So that's exactly my next point, that the superstrata, but they match many properties, which is unexpected. Again, they're not typical states, but if you look at the mass gap, for example, they do get the typical state mass gap. If you look at the thermalization, for example, they do get the typical state thermalization. So they get many properties of the black hole. They're not typical, that's my next point. And then, yes, go ahead.
Could you clarify what kind of checks have been done regarding the CFT dual state and in what context?
Oh, so the CFT, there's a whole industry of that. Rodolfo is around, right? I don't know. Rodolfo is around. So, yeah, there's a whole industry. So you can actually, so the dual states are known. There are some 0-0 strands and some ++ strands. You can compute, for example, 3-point functions. So you take so this is dual to a heavy operator in the CFT, and you can compute heavy, light. You can compute that, and in the bulk it's very easy. Just you look at the normalizable mode coming out of this structure at infinity. You read of the coefficient. You do holographic normalization a la Taylor and Skanderis. So it's a horrible game. Those guys do it, and then you match in the CFT. You say I have a state in the CFT. You go to the free orbital point and you compute the 3-point function.
Is it at you mean the CFT at the symmetric orbital
yes.
point?
So the CFT, the symmetrical orbital point, you compute the 3-point functions, and then those are protected, and then therefore, and they are reproduced exactly by the bulk. And I think there's an infinite family of them which are matching. So it's really like an infinite number of checks which have been done for the supergravity duals. You can really do, right, Rodolfo?
In general, you would expect the symmetric orbifold theory to have more states than you would get in the gravitational regime.
You can build more states, of course, at the symmetric orbifold regime, and then some states are lifted and so on. But those are not. Those are protected, and they actually. So we can identify the state at the free orbifold point, and then again you compute an infinite family of 3-point functions. You go to the supergravity dual. You do holographic normalization. You get this infinite number of 3-point functions. You put them next to each other. They match. It's really a perfect matching. So It's really shocking. Roberto had a question, and then you can go to Chiming.
So these are supersymmetric solutions.
Yes.
In what sense do you get thermalization and chaos?
I'm coming to that. Just hold on two more seconds. I'll come.
So you talk about the three-point function involving superstrata. Are those three-point functions also protected?
I think so. Yeah, those are. Even some four-point functions are also protected, but it's a much harder game. The three-point functions which are protected, they match perfectly. Some things which are not protected, they also match, which I would have expected. For example, the mass gap. The mass gap is really the energy, the difference between the ground state and the first one. That's a non-supersymmetric object. But they're still protected. They still gives you the right answer in supergravity as in the CFT, even if, it doesn't have any right to be protected. So some things are protected even if personally I don't understand why. But again, Rodolfo is the man. So.
I was just going to add one comment. There are two people, at least here, who are experts in the precision holography of this. There's Rodolfo and David here. And I think, I've been told by colleagues that it's one of the best checked holographic dictionaries out there, even including QCD, N equals 4 Yang Mills.
I think enough has been said. Let's continue.
Okay, so one thing which I want to get as a side discussion, you can also do these solutions. You can also take a limit of these solutions when you construct them, and you can actually obtain asymptotically ADS2 solutions. So you can take this structure here, and you can take the limit of the solution when you throw away some of the ones in the harmonic functions, and you can construct, just from first principles, solutions which have asymptotically ADS2. So here they are asymptotic to Poincare ADS2, and here they have some bulk. The ADS2 space closes. And those states are dual to states of the CFT1. I think Ashok had some paper long time ago. He was saying there's a CFT1 dual to ADS2, which have some states which reproduce the black hole entropy. Those states are some of the states. These solutions are dual to some of the ground states of the CFT1. Now, the ground state of the CFT1 is very interesting because there are many people discussing the CFT1 dual to ADS2. There's a whole industry and so on. Problem number one, these ground states, all of them break conformal invariance. So this is one thing people who do CFT1 normally look around global ADS. These ground states of the CFT1, which are all supersymmetric, they all break conformal invariance. Moreover, they all have excitations. You can actually look at excitations around them, both in perturbation theory. You can also do the full back reaction. That's what Pierre and Anthony Hoop did. You can actually do the full back reaction, and you can show that this back reaction preserves, these non-supersymmetric excitations preserve the ADS2 asymptotics. So these solutions at the bottom, they really have dynamics. But again, they are the ground states of the CFT1, which is dual to ADS2. And because they have dynamics and because they have non-trivial excitations, there's an argument which Mikhail Pavlos made, which I cannot reproduce, but I can explain some details about it. You can show that because this ADS2 has all these excitations and conformally breaking ground states, this ADS2, the theory dual to this ADS2 is not a topological theory. Many people say ADS2 is dual to a topological CFT1. Well, the CFT1 is not topological. The CFT1 is actually not a topological theory. And then because the theory is not topological, you can also argue that it doesn't have any conformal invariant ground states. This is the argument by Miguel Pavlos. And therefore, the uncapped empty Poincare ADS2, so if you take an ADS2 which is uncapped, like the one of the BTZ throat, so just take an empty ADS2, that one is not dual to any of the ground state of the CFT. Essentially what this argument is saying is that all the CFT1 ground states, all the supersymmetric ground states of the CFT1 break conformal invariance, and the solution which has conformal invariance is not dual to any ground state of the CFT1. So this is again an argument which one can make, but there are some caveats about how to do the right functions in the CFT1. So this is something which we are discussing and so on. But it looks like this is going to be the story for this ADS2. The ADS2, the CFT1 doesn't have conformal invariant ground states. The Poincare ADS2, empty, uncapped, is not dual to any ground state. And in a sense, it's similar to ADS3. The Poincare ADS3, empty, uncapped ADS3, is not dual to any of the ground states. The ground states are dual to this, the Ramon vacuum are dual to some other objects. And there are many claims that people say the CFT1 doesn't have excitations because you cannot put excitations on top of ADS. Yes, if you look at the wrong vacua, which are again the one which have an infinite throat, they have no excitations. But if you look at the right ground state, which breaks conformal invariance, it has excitations. So the CFT1, the CFT1 dual to Poincare ADS2 is really a nice, clean, beautiful CFT1, which has all the right properties you have. You have states, you have excitations, and you can work with them. So this is a side comment based on these solutions. You can just build these solutions from scratch. One could have built them 20 years ago, long before all these games about ADS2 appeared. And there's a story here. So I just wanted to mention it as a side story. Why are they not collapsing? The reason is very simple. If you look in 5 dimensions, all the solutions have bubbles, and they have 2 cycles. The 2 cycles have flux. When you put flux on a bubble, then there's a kinetic energy. There's a potential energy, there's a kinetic energy. When you have some bubble, some topological bubble, and there are 17 units of flux on it, when you make the bubble smaller, the energy becomes bigger. The energy of the flux is always the number of flux units divided times g theta theta with the legs up. And therefore, you can say that when the bubble becomes smaller, the energy becomes larger. So in a sense, when you put bubbles on fluxes, when you put bubbles on fluxes on bubbles, the bubbles don't want to collapse, they actually want to expand. And there's a nice balance between gravity, which pulls the bubble together, and on the other hand, and these fluxes which want to expand the bubbles. You really have a nice balance between them, and this is the collapsing mechanism. There's a side story which one can do with the charge budget, and this is the inspiration for the Tadpole conjecture which we got. I'm not going to get into this. This audience probably, except Mariana knows about it, but she's a co-author of the paper. But many people in the audience, I'm not going to get into this. So okay, great. We have all these 20 years of microstate geometries. We have a nice, beautiful, huge amount of solutions. Bubbling geometry, superstrata, largest class of equations, solutions to Einstein equations. Fireworks and happy stuff. But they have many features of typical microstates. But as Roberto and I were saying, problem number 1, they don't have the black hole entropy. If you compute the entropy of these solutions, they don't have the black hole entropy. They have a huge amount of entropy, much more than I would have ever hoped. The entropy is over the Q1, Q5 to the power 1/2 times Qp to the power 1/4. In CFT language, they correspond to putting L-1s on these D1D5 states. They don't correspond to putting L-1 over N1 and 5s on the CFT. So in CFT language, we understand why they don't have the right entropy. In the bulk, we also understand. There are some papers by Masaki and also by Masaki and Daniel, which explain why this entropy of these guys is smaller than the black hole. Moreover, we have a very tenuous link with the only 5 states which count the black hole entropy. It's very hard to identify. Given a supergravity solution, it's very hard to identify what's the dual state. Again, as Nick was saying, there are 2 people in this room and maybe 5 people on the whole planet who can do this stuff. It's horrible. This holographic normalization, it's really something like, I think, again, it's really like, I think there are 5 people on the whole planet who can do this stuff. It's really a horrible, horrible thing to do this precision holography, and, it's really hard to understand, to do these things. It works, it gives you amazing results, but it's very, very complicated. It's not something which, I could do or I could put a grad student to do. Maybe I can, maybe I can put Raphael, but okay, that's a different. And moreover, we have a problem. In a sense, the momentum modes which give the D1D5 entropy are quantized in units of N1 and 5 times 1 over Ry. And they are fractionated states. Again, they are due to L-1 over N1 and 5. And the problem is the dual of the fractionated momentum states are very hard to build in supergravity. We have some attempts. Masaki has some trials. We really tried in the D1D5 system to build these fractionated momentum states in the bulk. It doesn't seem to work. It doesn't work. I don't know if there's a fundamental problem or if it's something technical. So that's one thing. So the painful reality is that for 20 years we have these solutions. We have these nice beautiful results. We understand things very well as a result, but we have not succeeded to track down typical D1D5 Stromer-Javafa microstates from the zero gravity regime where they give the entropy all the way to the to the finite gravity regime where the black hole exists. And again, you can say, is it technical? Are we just, we can do horrible supergravity solutions, but we must have some base, some space sense, some co-Fouriering. We have some techniques to build these solutions. They are horrible solutions, cohomogeneity 5. So, not anybody can build them. Maybe we just need to be technically much more stronger, and, we'll find all of them if we're just technically much more stronger. Or is it, is it a fundamental problem? So somehow, maybe in the bulk, you can only build some solutions, and, the other ones you cannot build. Maybe it's technical, maybe it's not. I don't know. I'm still of half mind. Moreover, we have bubbling solutions which have a horrible hyperkähler base space, which have multiple bubbles and so on. We have no idea what their holographic dual is. You cannot build superstrata on them. You can also build hyperkähler things. We don't know. We really have a huge amount of solutions space out there where you cannot build solutions, first of all, and we don't understand the holographic dictionary. So there could be that all the Stromer-Javafa states will be somewhere in that corner, and we are just not powerful enough to do them. But I don't know. And this is something which has been bugging us, and we don't know if we're missing some ingredients to get these fractionated modes. And again, this is something, so the field we have been stuck for quite a while. Now, I'm a Romanian, and we have a Romanian proverb, which is, do not pray to the saint who doesn't help you. I don't know if other countries have it. I don't know, maybe some Catholic countries have it also. But we have this proverb like, you don't pray to the saint who doesn't help you. So this thing, D1, D5, works very nicely, but at some point, it looks like we're at an impasse. So then we said, okay, instead of looking at a D1, D5 system, look at D2, D4. It's a T-dual system, right? You know, what can be, it's not harder than D1D5, but somehow its properties are fundamentally different than D1D5. Somehow the way fractionation happens and the way the entropy of the black hole comes about is fundamentally different and seems to be much more friendly with supergravity. And the way to understand this system, I mean, again, you can look at the D2, D4, so you can think about this as D4s and those as D2s, or you can take an F1 and S5 in type 2A and you can uplift to M theory. It's the same, it's the same system. So if you look at an F1 and S5 in type 2A, when you put an F1 inside N5 and S5s, the F1 can actually break up into N1 little strings. Into N5 little strings. This is shown a long time ago by Dagra, Verlinde, Verlinde. When you uplift to M theory, these little strings actually become strips. So an F1 becomes an M2 wrapping the M theory direction. So this is the M2 here, here, here. But you see the M2s don't have to stay at the same point. Between two M5s, which are again the blue guys, the M2s can actually behave independently. And moreover, the M2s can actually have their own momentum waves. Ishan gave a talk last year about this at the conference here. So you can actually build these things, and you can ask, okay, how do I get the Schrödinger entropy out of this system? The answer is simple. Each M2 strip is a point inside the M5, and therefore it can oscillate in four possible directions. So there are 4 bosonic oscillations. There are 4 fermionic partners. So in the CFT entropy, there's a factor of 2. And then you have N1 and 5 strips, because again, every M2 becomes N5 strips, and you have N2 total M2s. So you really have N1 times N5 strips like this, and all of them can carry momentum, and you put momentum on all of them, and you use the Cardy formula, and you get the black hole entropy. So you get the black hole entropy from this kind of configurations. Again, this was known by Dagra, Verlinde, and many people over the years used it. Emil, for example, has been banging our heads for many years that we should look at this system instead of looking at D1D5, but we didn't listen. So now we are coming to his wisdom. This is but this picture is very nice and beautiful. But this is the zero coupling picture. This is the picture which ignores brain interactions. When you have brains ending on brains, and we know that when you have brains ending on brains, it's not that simple. When you have, for example, when you have a D1 ending on a D3 or an F1 ending on a D3, the F1 or the D1 pull on the D3. They actually make a spike, and this is called the Kallan-Maldacena spike. It also this paper by Rob Myers and collaborators of Tashford and I forgot who the other person was, which discussed this, the D1 inside the D3 Constable. And essentially so the D1 pulls on the D3, makes this spike, and the M2s ending on the M5, they're also going to pull on the M5s. They're not going to stay there happily. The M5 gets deformed by the M2 into this shape. So for example, you have 2 M5s and an M2 in between. The M5 gets deformed into this M2, and this M5 also gets deformed. So you get this kind of structure, this kind of a spike. But it's not really a spike, because there's a common M2, M5 direction. So there's a common M2, M5 direction. These M5s and M2s, again, if you think about the D1, D5 or F1 and S5, there's a common D1, D5 direction. There's a common F1 and S5. That's why we put momentum at the end to get the black hole entropy. So there's a common F1 and S5 direction. So this curve is actually not a spike. It's more like a furrow. It's more like a valley. And on this valley, on this furrow, you can actually put momentum waves. And the momentum waves can be put, you can actually turn them on by putting some fluctuations. You can get this furrow, which again, I'm looking at this segment of this thing and I'm multiplying by the y direction, which is the common M2, M5 direction. So this is the way this object looks like. So this is the y direction. And I have a momentum wave, and those are the torus directions, and this is the direction of the M2 brain, which is x11. So on this spike, on this furrow, I can actually put momentum waves, and you can look locally. You can look locally on this momentum wave, and you can say, these momentum waves look like they have M2 charge, M5 charge. So this solution looks like it has M5 charge, M2 charge, and momentum. But if you look locally, it has some other charges. It actually has some other dipole charges, which are local charges, which you don't see far away, you don't see globally, but they're actually going to be here. So for example, I have an F1, this direction carrying momentum in this direction, but the F1 bends up and down. So there's an F1 charge going this way locally. There's also here it goes the other way. Globally it integrates to 0, but locally I have extra dipole charges on this beast. And in this particular case, what we found is that the beast has actually 6 local dipole charges. And as a result, when you zoom in on the beast, when you zoom in on this animal, what you find is that the supersymmetry of this guy. So this guy normally has 4 supercharges because it has, it's a D1D5P system, dualized a bunch of times. So it's an F1 and S5 or M2 M5 T-dualized. So it's a system of 3 brains which have 4 supercharges. So globally, this guy has 4 supercharges. But if you look locally, what you find locally is that this guy, when you look here, the supersymmetry gets enhanced from 4 to 16. And wherever you go on this thing, you have 16, but they're different 16. Here you have some 16, some 16, some 16. Only 4 are common. Only 4 are common, but globally there are only 4, but locally there are 16. So this is like a local supersymmetry enhancement, and this is the smoking gun of smooth horizonless solutions. Just to give you a brief history, long time ago, Nick and I found these bubbling geometries, which were basically, back in 2006, almost 20 years ago, my God, which were like, some bubbling geometries, which are smooth, and, all the frames, they are horizonless. And then Vijay and collaborators, and Tommy Levy and Per Berglund, they actually said that no, those are actually, when you dualize them down to type 2A, they actually become multi-center D6 branes with flux. And these multi-center flux D6 branes, they are part of these DNF solutions. There's a special class of these DNF multi-center solutions. And these guys, if you look locally on every D6 brane, there are 16 supercharges. The D6 branes have a billion flux, so there are 16 supercharges locally, here. Globally, there are only 4. Each of the branes has 16, but there are only 4 in common. So the solution, this DNF solution, this bubbling solution, which is uplift of the DNF solution, has 16 supersymmetries at every center and 4 globally. And this was actually the smoking gun of having a smooth solution. The smoothness in 11 dimensions corresponds to 16 supercharges locally in 10 dimensions. This seems to be this was the game. The entropy, of course, is much more than the black hole. Jan de Boer and Shearer, Schauk, and Dieter van den Bleck and Elias Messama counted it. It doesn't work, but it's a small entropy. But still, the idea is smooth solutions, 16 supercharges locally. Then we did another paper, about a few years afterwards, where we put one of these guys to fluctuate, we put a super tube. Again, same phenomenon. Smooth solutions means 16 supercharges locally. For the superstrata, when we conjectured them with Pasaki and Jan and Nick, we said again, we had the same principle. 16 supercharges locally, 4 globally. We conjectured them, and then, we found them to be smooth. There seems to be this thing historically, again, maybe that if you want to get a smooth solution in some duality frame, that smooth solution, the smoking gun of having a smooth solution, is actually having 16 supercharges locally and 4 globally. This is again our experience for all these years, and we call this guy a Temelion. A Temelion is like the fundamental building block. We wanted to call it something else, but if we have a good wine during a wine and cheese, I'll tell you how we wanted to call it. Anyway, so this is called a Temelion, and it has this structure: 16 supercharges locally, 4 globally, and this seems to be equivalent to build. So when you have a system of branes like that, that's going to give you a smooth solution. If you have something else, it will give you something with the horizon or something with some other problems. So this is the story with this system. And you can get the entropy of the supermaze. It's actually quite simple. You can actually ask how much entropy do you get out of this thing. And again, the simplest is to put a D2, D4. So you have a D2 between 2 D4s. There's a momentum wave going in this direction. And you can ask how much entropy is there in this system. You can actually argue that you have bosons, which correspond to the D2 moving inside the D4. And these bosons don't have any R charge. So when you excite all the 4 bosonic degrees of freedom, you actually get microstate geometries which don't break the SO4 symmetry of the black hole. So the black hole is spherically symmetric, and the microstate geometries are going to be spherically symmetric as well. You don't break the R symmetry of the black hole. And this is something, again, which Ashok has been beating us over the head for 15 years. We kept on getting these microstate geometries which have superstrata, which have a big structure in space-time, which breaks the black hole R symmetry. And Ashok has been saying for all these years, no, the entropy should come from things which don't break the R symmetry. Again, we didn't listen to him, like we didn't listen to Emil, and now we're coming back to his wisdom. This momentum is carried by the waves, and again, if you look at the bosonic degrees of freedom only, which again respect this SO4R symmetry, you actually get a huge amount of the black hole entropy. You get 4/6 of the N1 and 5 of this of the Strominger entropy by just looking at things which are spherically symmetric. I think there are also 2 fermionic degrees of freedom preserving this SO4. So in total, there will be 5/6 of the entropy, which is going to come from spherically symmetric configurations, very different from the superstrata. The superstrata break this spherical symmetry. These guys have 0 angular momentum, 0 R charge, perfect spherical symmetry of the black hole, but they do garbage on the internal directions. The internal directions are all going to be messed up by these things. Yes, Emil.
So to get this counting, you need of order N1, N5 of these intersections to be populating the T4.
Yes.
So that's a very tiny sub-Planckian packing of the stuff on the T4.
If you ignore back reaction,
why are
yes.
it seems like a geometrical description would be
I'll come to that in 2
impossible.
seconds. I'll come to that in 2 slides. Absolutely.
So this picture that you have over there with the bions and these things, is this with self-gravity?
Not yet. So at this point, I'm just doing brains, which are pulling on each other.
So then this is not different than any of the calculations that we do at with coupling.
It's a bit different because people at weak coupling, they don't look at the bending of the brains. So at weak coupling,
Well,
everybody
yes.
says I have a D2 between two D4s, and everybody's behaving as if it's a straight D2 ending on a D4.
Yes.
Now we are saying, no, it's not. And moreover, at weak coupling, what you can do, you can show that these momentum waves, they actually preserve you can actually build a momentum wave at weak coupling. That's what we did with Rafael. I'll explain on the next slide. And you can argue that locally, it preserves 16 supersymmetries. So nobody has done a weak coupling. So in a sense, we are going a tiny bit away from weak coupling. We are looking at the interaction between the ingredients, and we are finding the 16 supercharged structure at weak coupling at the level of the brains. And the point is, we want to do super tubes and we want to do many things. Super tubes, for example, at the beginning, we did them at, Mateos and Townsend did them at weak coupling. They found a 16 supercharged structure locally, and then, you guys came and, you did the back reaction of the same brain object, and you found, this is going to be smooth. In the D1D5 frame, it's a smooth solution. So the 16 supercharged structure, which you find in the brain construction at weak coupling, that seems to be the equivalent of smooth supergravity solution when you back react.
Yeah, but so you can quantize the super tube, the Born-Infeld description,
Yes.
and that's something that people did, and then they got their right entropy. So what you're doing is analogous to that. in this case.
What we're doing is analogous to, this is, it was done before us by Dagravel and Evelinde. So they just said, okay, you have a D1, D5, I have a D2, D4 system or an M5, M2 system. You have all these strips, you put momentum on them. It's a very simple counting. I'm not even quantizing anything. I'm just saying, okay, I have a strip, I have N2 and 5 carriers in a CFT which has 6 degrees of freedom per carrier, and therefore I'm going to get the entropy of the Stromanov-Alpha. So it's a very simple argument they have in that paper.
But there's no supergravity solution.
Not yet. I'm coming to that. So at this point, this is a brain construction with 16 supercharges locally, which is again the smoking. Again, for us this was the smoking gun before. So, but indeed, there's no supergravity solution yet. Yes.
Yeah, one question. So suppose that you want to test the idea that the missing entropy comes from other solutions not captured, so some other corner of the parameter space, and those solutions are known only numerically, so there is no analytical representation. So is there a way? Because eventually you can build just one solution at a time for each parameter space. Is there a way to count the number of
No,
states
but there's
numerically?
smoking guns. So for example, if you build numerically a solution, then I give it to Rodolfo or to David or to somebody, and you can ask in the CFT what is it dual to. And if, for example, you say that this solution in the CFT is dual to, in the D1E5 frame, is going to be dual to fractionated momentum carriers. So momentum carriers which have a 1 over N1 N5 or 2 over N1 N5 momenta. So the momenta in the superstrata are quantized in units of 1, 2, 3. When you have N1 N5 D brains, the momenta can be quantized in much lower units. And that's something which people can actually calculate using precision holography. So if you give me a solution numerically, if we get some friend of ours to do a solution numerically, then we run it through this precision holography, and then we can actually show that it has, if you show that it has 1 over N1 N5 fractionation, that's a smoking gun that you're in a good parameter space. So that's something I can do. Even if I don't count, the moment if I only could get such solutions, a bunch of them, I would be ecstatic, even if it's numerics. So again, the other degrees of freedom are going to be breaking the SO4 invariance, I think. And that confirms the expectation I had in a paper with Masaki and Nick. So somehow everything seems to be working out. You have some degrees of freedom which are torus degrees of freedom, they keep the space-time SO4 invariant. You have some degrees of freedom which mess up the SO4, which break up, which extend in the transverse space. The question is, how does the solution look like? Well, the answer is very simple, not very simple. The system, the two charge solutions of M2, M5, for example, they are governed by some Monge-Ampere equation, which was found by Lunin back in 2007, and the solution is cohomogeneity 3. It's a supersymmetric solution, but Monge-Ampere is a nonlinear equation, a horrible nonlinear equation, so the solutions depend on 3 variables. The 3 variables are, again, on the torus, you have this M5 direction, so we can just put one direction on the torus. The M3 direction is another one, so this system here, there are 2 variables in the M2, M5 plane, and then you have the radial direction out. At least 3 variables. If you don't have 3 variables, you lose physics. Of course, if you smear on the torus, you'll get the black hole. If you smear on the M3 direction, you get the black hole. You can always smear, but when you smear, you get the black hole. You never get, if you want to get microstructure, you have to keep things, you have to avoid smearing. So it was shown by Lunin back in 2007 that if you just put some brain sources, you actually get a solution. This is just, there's a one-to-one map between, so he said, if you look at the brain sources and you look at this Monge-Ampere, you can prove that the solution exists. But I don't have a solution. We're nowhere near to find a solution. This Monge-Ampere is a horrible nonlinear equation. And moreover, you expect naively that the supergravity solution, when you put momentum, is going to be a link to cohomogeneity 4, because you put momentum also, so you have a function of the moment, so there's a momentum direction y, so the solution depends on the torus direction, m0 direction, out of the board radial direction, and the m0 and the momentum direction. So 4 variables, cohomogeneity 4, horrible Monge-Ampère. Life seems to be hard. However, again, there's another Romanian proverb, to the blind bird, sometimes God makes the nest. I don't know if, again, that's more Romanian. Probably less people have this proverb. And the point is, if you zoom in on these brain profiles, if you take a scaling limit of these brain profiles, and in particular, if you take a simpler example of an M5 with an M2 spike, you can actually show that, and that's what we did. And in a previous paper, and also we are doing it right now. You can actually show that these solutions, the zoom in on these solutions, gives you some ADS3 times S3 times S3 times Riemann surface solutions, which were found long time ago by Bacas, Estes, Docker, and Krum. And it was actually Eric Docker and John Estes and Daria Krum who did them. There's a whole industry going on at UCLA for many years. And then John Estes and Daria came to Paris, and Kostas joined them. But there's a whole industry building these solutions. So there's a Riemann surface, ADS3, S3, S3, and basically you can show that this Riemann surface solution is really a zoom in on this M2 M5 system. When you have an infinite M2 ending on M5, if you look at the solution, you zoom in some region, there's a Riemann surface. You get one of these solutions. Of course, the coordinates are all screwed up. The coordinates are horrible. The Riemann surface coordinates are some messing combination of the brain coordinates. For example, in this system, you can put an M2 brain which doesn't feel a force, a floating M2 brain. The system is an M2 ending on an M5. So this dotted thing is an M2, which you can put as a probe. Nobody stops you. It doesn't feel a force. You can ask, how does the M2 look like in this Riemann surface? Well, it's this equipotential of this horrible thing here. So it's really a horrible set of coordinates, but the equations are linear. The equations for this thing, the equations governing this thing are actually linear. You go from cohomogeneity 3 Monge-Ampère to a system of 2 variables, and then you can actually get a linear solution. And what we showed is that all these solutions of Bacas, Estes, Docker, and Krum, they give the back reaction of this kind of mohawk. We also build, as I was telling Roberto, we also build the equivalent of the momentum wave on the supermaze, so you can actually build a null momentum wave. And what we found recently is that you can put the momentum wave on the supergravity solution by following a linear algorithm. So you can actually find a known, you can solve Monge-Ampère if you're very powerful, or you can take one of these solutions and you can reinterpret it as a Monge-Ampère solution. And then given that solution, you can add momentum using a linear algorithm. So you don't have to, so adding momentum doesn't screw up the rest of the background. It's really something which you can put, you have a background, solving some equations, and on that background you can put momentum, and you don't screw up these equations. It's really something which one can do linearly. That's something which was quite unexpected, and the net result is that, if you do that, you're basically solving some functions, and you can put the momentum in some arbitrary function of the null coordinates. The point is, at the end of the day, if you are careful and work in the right limits, you actually solve cohomogeneity 2 solutions. So you can actually do it. You can actually build solutions which have all these features. They have a bubble, they have momentum, they have M5s, and so on. We haven't built them yet. We are really at the level of, we found this linear algorithm, and we just understood how this mohawk of M2 M5 solutions is linked to these things. We are just understanding currently what's going on here. But the point is, again, coming back to the back reaction, the point is these solutions have, so you can ask, okay, how do the solution look like globally once you back react them? These M5s, because I have some M5s, the brains, when you back react, the M5s contract the direction they are wrapping. When you have a brain, always the metric parallel to the brain goes to 0. So when you have some system of M5s and M2s going on like this, for example, again, 16 supercharges locally, so there's no horizon. But when you have a brain here, for example, and you look at back reaction, there's something called the geometric transition. The brain actually goes to 0 size when you back react, and the dual cycle becomes large. And what you end up having, for example, you have these M5 brains here, there'll be a dual cycle, so this blue segment will disappear, because again, the metric next to the brain goes to 0, but there's a blue segment which is going to become large. The M2s, again, there'll be no more M2s, but there'll be a 4 cycle there'll be a 3 cycle times a 4 cycle, which is going to become large, which will be a 7 cycle, which will capture this M2 charge. So there's some numbers here. They're like, 7 M2s, 3 M5s, they form a bound state. So these numbers are going to be preserved. Here you'll have the fact that you had 7 M2s here, there'll be 7 units of flux on this bubble. And moreover, you have some other bubble, because when you have a contractible cycle, and you back react the branes, there'll be a bubbling transition and you'll get some other geometries. It's a bit like in the LLM solution. It will be more complicated than LLM, but the way you go from giant gravitons to LLM solutions, it will be the same. It will be the same thing. And again, and the question is, how is it going to look? As Emil was saying, I have N1 and 2 beasts. I have a torus which has like, Planck, size of like, 20 string sizes. And I'm building N1 and 5 little guys inside it. So the question is, why is it going to be singular like hell and, blowing up and, break supergravity and so on? The point is, when you have many brains and you put them together, these bubbles become large. The bubbles have no idea they're inside the torus. This M5 brain, when I have 20 M5 brains here, there's this S4 here, which has size, 20. That size is frozen. That bubble is frozen. So if I put my M5s and 2s in units of like 20, all the cycles will have size of order 20. So even if everything in the naive brain construction is crumpled up and small and tiny and so on, once you look at the full back reaction, this actually should become big. That's my expectation. But again, this is hopes. So that's why I called the paper is called hopes, because this is a hope. We don't, we're trying to build it right now, but I have a hope that the back reaction is going to make the bubble large, at least some of them. So the hope is that using this, I'll get at least N1 and 5 NP over some number, over 20 of the entropy by doing this, which is much more than what we never do. But that's again my hope. There's a question about the holography of this. 5 minutes, okay. There's a question about the holography of this. The problem is, they have torus mode, KK modes. And if you look at these solutions holographically, if you put them in ADS3, for example, if you build these solutions which have torus garbage, they correspond to some operators which are very weird. They have dimensions which goes like Q5 times the number of the modes times divided by L1, where L1 is one of the torus distances. They're very strange operators. From an ADS3 times S3 times T4 perspective, these operators are not captured at the orbifold point, but they are the ones which will distinguish different microstates. If I give you one microstate which has some D2, some D4 inside the torus, and some other microstate which has some other D2 and D4 inside the torus, they will differ by webs of such operators. They will not differ by normal. I mean, again, they are spherically symmetric, so they look. I mean, all their spherically, all their nice ADS3 times S3 times D4 fields are going to be the same as those of the black hole far away, but they'll have these extra operators. And the question is, can you understand these operators? Can you actually can you do holographic renormalization with them? I don't know. It's something which I don't know. I keep on asking CFT people, all the CFT people, Eric, I ask him, and all the people who do CFT ask them, in the D1D5 CFT, can you see these beasts? Can you see these operators? Can you find some, maybe they are not renormalized, maybe they are not protected, I don't know. But this is what's going to distinguish microstates from other microstates. This kind of webs is the webs of these beasts. It's not going to be normal ADS3 times S3 times T4 beasts. And again, that's a confusion I have. So the hope of this thing is that, again, you can take DVV microstates, you look at brain interaction, you see the super maze, the brains pool and merge 16 supercharges locally, you turn on back reaction, and you'll have, again, some microstate geometries which have T4 KK modes and big bubbles and so on and so forth. Again, do you need 6D supergravity, 10D supergravity? I don't know, but what will happen is that this is the way to track the entropy. So this is, again, the big hope in this thing. Non-extremal microstates are going to go much faster, and there's a talk by Pierre by them. You can put them by putting a tiny bit of brains as probes. You can build a non-extremal microstates by taking a supersymmetric one and putting a brain, an anti-brain probe in it. But this is you can do this in the probe approximation. But the problem is, it's very hard to do the back reaction. Pierre recently has shown with Ibu that if you actually have no supersymmetry and no rotation, you can actually factorize the equation, so you can actually build Schwarzschild microstate geometries, which look like bubbles, which have positive and negative flux. Those things, you can actually show that they're really bubbled brains and anti-brains. They really have brains and anti-brains, which actually have bubbled up into something. So they really have this brain anti-brain structure. These solutions, you can build asymptotically flat ones, asymptotic ADS3 ones. Pierre is going to talk about them. You can compute the RT entropy. It has the right features at small angles. It gives you some value which is the right one. At large one, it matches the most entropic configuration. You can check that they have the right features. You can also build non-supersymmetric things numerically, and those are called microstrata. Nick and Anthony and Bogdan Ganche build them, and Stefano and Rodolfo analyze them and work with them to find the CFT dual. It's using a consistent truncation done by Daniel and Nick and Robert Walker. It's much more complicated, but the CFT duals are known. The CFT duals of those guys are known, and the CFT duals are really, you have a D1D5 system, you put P left, you put P right on top of each other. When you're asymptotically ADS, this doesn't decay, but in flat space it should decay. So those are some non-extremal microstates. They are dual to this particular combination of CFT operators. So you see an L-1 and you see an L-1 tilde. So they're actually non-supersymmetric. They have right movers and left movers. You can do them numerically. You can barely get them above the black hole parabola because you begin from the NS ground state and then you build them, and it's very hard to get them above the the black hole parabola. The Bar-Heinemann solutions, at this point you cannot. Maybe Pierre has already found. I mean, no. A month ago when I talked to him, the ADS-T ones, he couldn't get them above the parabola, but I think he's working on that. So I think maybe in his talk he already solved the problem. Anyway, this is the story. So we have this the Bar-Heinemann solution, which are like really bubbles, non-supersymmetric, which really correspond to brain anti-brain. These solutions, which really momentum anti-momentum, but that seems to be the story. I'm not going to get into this again. Anti-brains, usually they have instabilities, and these solutions could be unstable. Pierre solutions could be unstable. The microstrata, when you put them in flat space, they could be unstable. But the instabilities are expected because they correspond to Hawking radiation. You really have left movers and right movers, and in flat space they can annihilate and they can emit a closed string and they can actually decay. And this is actually shown by Samir a long time ago that in the JMAR solution, which is unstable, because you have open strings going to the right and to the left, they can meet as a closed string vertex. They can emit a closed string, which is the equivalent of the Hawking radiation. But because they are coherent states, that's why they actually decay much faster. And in a sense, from the anti-brain perspective, people have all these de Sitter instabilities, which are swampland, which are conjectured. These appear very natural from a black hole perspective, because from a black hole perspective, these guys should be unstable. The instability should be there. When you put anti-brains and when you go to non-extremal, you should get instabilities, again, using Samir's arguments. And therefore, these de Sitter instabilities, they are very natural from this perspective. Mass gaps and chaos, you can calculate these solutions. Again, you have the supersymmetric ones, and then you can put excitations on them. So you can put some tower of excitations on top of one microstate, another microstate, another microstate. And the story seems to be that, at zero coupling, you have a huge amount of them. And then when you increase the coupling, at the first level, you get a bunch, very closely spaced. But then you start getting mixing, because again, all these microstates can mix, can tunnel into each other, so you get mixing. So you'll get a spectrum, which is, 0, and then you get a gap. And then you get nothing, and then you start getting some density of states. You can also show that if you compute the 4-point functions, again, 2 light operators in this heavy state, you get a black hole thermal decay. Whatever you put goes into the black hole, and then after a long time it comes out again. So you really get this echo coming from this thing after a very long time. And what I want to so when I gave a talk in Santa Barbara, I didn't. So there's like this paper by Helman, Shuturiach, and Zhao, which actually had some picture with the spectrum, which is really all the guys at zero entropy. So those are those guys. You get all the black hole entropy at zero entropy. Then you get a gap. Again, you get a gap from here to here, and then you start getting states, and the states are going to be mixed to each other, and you get a curve. And what I kept on asking Luca and Gustavo when they came to and Matthew Heinemann when they came to Saclay was like, why don't you guys see some bumps? Can you see some bumps here? Because I expect some bumps. At zero, I get the supersymmetric states, and then I have these guys the first level, and then I have another level, the blue guys, and they mix. And actually the spacings here are actually, I draw them a bit separate, but they're really of the same order. So there's a mixing between them, but the mixing, when I have a mixing of many states at the same energy, I should get some sort of bump with some width coming from the mixing. And then I saw the talk by Chiming Chan at Strings, and I saw these bumps. There's I guess the same story. Okay, it's done in a very different context, but in his calculation, I saw these bumps, and I was like, wow, So again, zero entropy, and then at some point there's a gap, and then you start seeing some states, more states, bump. This is the kind of structure I expected. Very low extremality, very close to very close to extremality. I expect this kind of bump structure. So that's when I saw this talk at Strings. This is copied from your talk at Strings, so he'll probably discuss in much more detail. But this is the kind of the bump structure which I want. Anyway, so again, the best I hope is, again, if we can get these classical geometries, there's a huge amount of them. The idea, again, the biggest hope is that we'll get enough of them to span the Hilbert space. There's a black hole Hilbert space, but the typical states in the Hilbert space, the hard typical states, will be some superposition of them in some way, so there'll be non-geometric, hard to do. Dynamics, tunneling, no geometric dual. How do you interact with such a beast? I have no idea. I'm confused. The only thing which I can do as a string theorist is to basically try to build all of them and try to see that this picture is indeed correct. So again, to summarize, I think I'm almost, 1 minute, okay. So we can track the states, at least for the super maze stuff, we can try to track the states all the way from zero coupling to full back reaction. Somehow the feature seems to be this Themelion feature, 16 supercharges locally, 4 globally, meaning no horizon. Geometric transitions, again, what I hope is that they're going to give us more solutions. And then for non-BPS microstate geometries, again, you have the solutions by Pierre and Nibu, and also the microstrata. The ones by Pierre and Nibu have really bubbles with plus and minus fluxes. They really have brain anti-brain structure. They really have this very nice thing, similar to the sitter proposals, but the full solution is known. Unlike the sitter solutions, where nobody knows the full KKLT geometry, here we know them. Here we have the whole bloody solution, so it's something which was useful also for the Tadpole conjecture. And the question is, again, we have classical solutions. That's what we can build and we can trust. Those are going to be basis of the Hilbert space. In the best of cases, there will be a base spanning the Hilbert space. Maybe it will be over a complete basis. I think Roberto will be talking about some other some arguments. You can get some other classical solutions which are going to be an over complete basis. My best hope is that maybe there will be a basis, but the typical states will be some superposition of those things. So the question is, what are the features? If we observe those things, if we can we get for modeling? If you want to model black hole microstructure, how are we going to do it using these solutions? And are we going to get some generic features? For example, tiled deformability, multipoles, deviating universal deviations. Any hopes for Lisa? We have all these hopes. And yesterday was a full day of this, and I really hope that using this one can get some universal deviations. But that's again a big hope. Thank you.
I wanted to comment in relation to the statement that the black hole solution is some sort of ensemble over the microstates. For the half BPS NS5P solutions, there is a well-defined way to average the solutions, and the result is not a black hole. And not even a black hole with a stretched horizon.
Indeed, but there's no black hole there either, so there's no black hole in the NS5P either.
There is, and you can define for it a stretched horizon, but the ensemble average is
it's not ensemble. So
different.
what I claim is actually it's not that the black hole. So what I claim is that the black hole solution describes the physics correctly far away, and at the scale of the horizon is not a good description anymore. It's the same as using fluid mechanics to describe shot noise. I cannot use fluid mechanics to describe shot noise in the room. I need to use molecules. So there's a scale at which fluid mechanics breaks down, and I need to use microscopics. And it could be, what you're saying is that if you do the real ensemble average, you're not going to get a black hole. The only thing I'm saying is that the classical black hole solution, spherically symmetric and beautiful, will break down, will stop describing the physics at some scale. This is the statement. Okay. But you're right, maybe the ensemble average is going to, it could look different.
Time for 1 or 2 more questions, if we have them.
One comment, but anybody else? Okay, just the other thing also in terms of transitions to chaos, when you break the supersymmetry, we find that anomalous dimensions of operators start emerging, and they depend non-linearly on the amplitudes of other fields. So if that isn't a signal of a transition to a chaotic spectrum, I don't know what is. And there's also, just to advertise, Anthony Hoop did a really nice calculation where we put it on a particular locus that we can get, which he managed to get to 11th order imperturbation theory in non-supersymmetric solutions. Bogdan got it to 1 part in 10 to the 50 and numerically. And when you break that locus, you suddenly get this transition to a much more chaotic spectrum where the frequencies shift and over time. So there's some possibly really cool numerics to be done there. But anyway, we see the transition to chaos when you break the supersymmetry, and we've got signatures of it.
Mm-hmm. Robert.
No. Do you mean random matrix statistics? What do you mean by chaos?
You have a microphone. No, you have a microphone.
Well done. So chaotic, I simply mean that the spectrum, what I mean by chaotic, we don't have enough spectrum calculated to see any kind of statistics of spectra. Maybe that's why numerics would be really interesting to do, where you could actually see a spectrum of something. But what you can see is that, the signature of supersymmetric is sort of rationally based high degeneracy ground states. What happens when you break the supersymmetry is that everybody's energy levels now become functions of everybody else's amplitudes. And so the spectrum will almost certainly resolve into low degeneracy, 0 or 1, with exponential gaps between them. And Anthony's calculation shows that the frequencies shift if you turn on this breaking term. the frequencies shift in time in complicated ways. Whether that's chaotic or not remains to be seen.
But generically, I think this chaotic stuff can be seen just because you have many eigenvalues and because you can tunnel bit. So these and these are just two different superstrata. They're like two supertubes. Where I can go from one to the other one, it's part of the moduli space. Of course, once I quantize, they are different states. But if I build some states on top of one supertube and states on top of the other, the mass gaps are not exactly the same. They are tiny. There's a tiny difference, especially the first one is more or less always at the same level, but the second one and the third one, they're equally spaced, but at different values. So here it's one value, here it's one value, but you can go from this supertube to the supertube, you can just tunnel between them. So therefore there will be a mixing between the blue guy and the blue guy and the blue guy and all of them, and you expect when you mix e to the s states, or like, in some small neighborhood, there will be a tiny mass gap between them, and you'll get a continuous spectrum, and you'll get the eigenvalue repulsion by the mixing. I think that's the expectation.
So just a quick follow-up on that. So when you break the supersymmetry, it starts causing one superstratum to start exploring the other modes that are available. So the picture that Iosif is painting is compatible with what I'm saying, just because supersymmetry breaking drives the mixing.
Is it quick? One last one.
Yeah.
Well, the question is quick. I don't know about the answer. These ADS2 solutions that you discussed,
Yes,
these are asymptotically
ADS2.
ADS2 times, so there's some 10-dimensional
Times S3 times S3 times T5. Sometimes.
And they're smooth in 10 dimensions?
Yes, they're smooth in 10 dimensions. And actually, even in 5, if you...
Okay, and the question was, what is the R charge that they carry?
0 in ADS2, hopefully. You cannot put something in ADS2 unless it has 0 R charge.
Okay, that was the question. So
No, absolutely. Yeah. So that's the whole point. So the point is, if you just build, okay, you can do them in two ways. You can either get microstate geometries in ADS3, which have an R charge, and then you can try to take some limits. Or you can say, great, I'm stupid, I just want to build ADS2 asymptotically. So I put the R charge to be 0 by hand, and I just build these guys, slam. And if I build them, of course, they cannot have an R charge because they have an ADS2 throat. So the R charge is 0 all the time. So there's no angular momentum, for example. You can see that here, if I have a flat space here, I'll get an angular momentum. But if I take the ADS2 solutions and I just kill the flat space completely, then I don't get any angular momentum. So they are clean 0 R charge. In a sense, they're doing what Ashok's solutions, Ashok wanted the solutions to do. You expect an ADS2 limit, if you want the microstates in the ADS2 limit should have no R charge. And that's exactly what you can do. Technically, again, it's the same construction. You just have to throw away some of the ones in the harmonic functions.
I propose we break for coffee and reconvene at 11:35. Let's thank Iosif again.